mute myself. Okay. Hello? Hello? Okay.
Good. Yeah, let me, okay. So that's just very brief introduction. So hello, everybody. Thanks for coming and join today's talk, Computer Architecture Seminar Series talk. Today's talk is from Dr. Yan Gu from University of California at Riverside. So Yan Gu is an assistant professor in the computer science and engineering department at the University of California, Riverside. He finished his doctoral degree at Carnegie Mellon University in 2018, and his bachelor degree is from Tsinghua University in 2012. Before joining UC Riverside, he spent 1 year as a postdoc in MIT. His research interest is designing simple and efficient algorithms with strong theoretical guarantees and good practice performance. He's the recipient of the NSF CAREER Award and the Google Research Scholar Program in 2024, and has won the Best Paper Awards at the PPoPP'23 and ESA'23. The best paper runner-up in VRDB'23, and the Distinguished Paper Award at SBAA'20. So take it out.
Thanks a lot. Okay, so yeah, today I'm going to share some of my recent work, and just want to make sure. So are you all in doctoral group or
okay? So hybrid.
Okay, yeah. So what would you work on? So I can adjust my speed and pace accordingly.
I'm working on some hardware, software co-design on some neural network.
Okay, I see. Okay.
Yeah, I think there are also some security architecture.
Okay.
Processing memory. Yeah.
I see. So
and also those two students are working with Dr. Hao Zhen on their parallel graph processing.
Okay. I see. All right. Okay. So I basically know. So I know this is computer architecture seminar. So so in today's talk, I'll still go with this page. I will now focus on it. There's quite a long delay, so that's it. So in today's talk, when I say the work of an algorithm is just the time complexity of an algorithm, and we would say parallel. Just if you have heard about it, it's just so-called work span model. Work is time complexity, the more operations, but time is something else. So we call it work span. It's the longest dependence chain. So that means if you have an infinite amount of processors, how long you can finish an algorithm. But this is not the key part of today's talk at all. I just want to, if you see maybe some other places I give the talk at theory groups, we may have, if you've seen this word, that is what they're referring to. Okay, so in today's talk, I'm going to talk about some parallel graph algorithms. So in today's world, I think this is computer architecture seminar. You probably know all these concepts: cloud computing, distributed computing, supercomputing, GPU, CPU. So even in today's, so almost nowadays, you cannot find a single processor machine, probably other than a toaster. So every machine is parallel. So even in today's talk, we mostly focus on the simplest form, is a shared memory multi-core processor, just every laptop, your phone, your desktop, everything. And then even for this simplest setting, we just want to know, okay, so we talk about graph algorithms that have been studied for decades. That's the conservative way. Some algorithms are over 100 years old, like Brufka's algorithm for MST, if you have heard about it, or if you go back all the way to Euler, all those concept of graphs and then graph algorithms that were maybe 250 years old. And so we have looking at it, and we have studied it for a long time for all these graph processing and all today's hardware. So the question is, are we mostly done? So interestingly, my answer is people don't really know how to do most of the graph algorithm, which is pretty surprising. So of course, there are definitely a lot of work on this topic. So before we talk about our work, we want to say, okay, the goal. Well, what do we mean by efficient algorithms. Okay, so in my word is have some theoretical guarantee. It's very fast in practice, and also it has to be simple because well, not always, but simplicity is a very good thing because it's you can cover them in even undergraduate courses, and everyone can try it, see if it works well in your application. Of course, some complicated systems also works, but in my goal, we want to achieve them all. And we don't know how to get this for most of the classic algorithms. So to start with, I'm just starting with the most typical and standard graph problems. You want to compute the shortest path on a graph, and you have a source. You want to compute the distance to other vertices, that call single source shortest path. Sequentially, you probably know how to do that, right? You can run Dijkstra's algorithm, one of probably the most famous algorithms, or definitely the most famous graph algorithms. Okay, so sequentially, that's very simple. Maybe 10 to 15 lines of C++ code, you can get a very good performance. If you want to improve that, you need to spend a huge amount of time and get some little bit improvement. Okay, how about the parallel setting? So because this is probably not the algorithm community, I would just let you know. So there is an algorithm called delta stepping, proposed about 20 years ago. It's a parallel shortest path algorithm. So the details are, so don't pay attention to the details because it doesn't work that well. The high level idea is pretty simple. So when you run shortest path, you put all the vertices in a priority queue, and then you just pop the elements, relax their neighbors, and doing that. So how can you do that in parallel? So you build this bucketing structure, and then let's say delta is 10. So I'm going to have bucket from 10 to 20, 20 to 30, 30 to 40, if that's my tentative distance. So I look at my first bucket, and then I use all these vertices within this bucket to relax their neighbors. Relax means you use your own tentative distance, add this distance, and see if it is smaller than the other one. If so, you update it. Okay, so then in this case, you're going to update these two vertices and then change their value and move to another bucket if needed. And then you just keep repeatedly doing so, and then keep updating. And then when you stop, and then you just keep updating. So you can stop when there's no updates within the same bucket. So you move to the next one, and then do the same thing until you finish all vertices. So in that case, by setting up this delta value properly, you can get these more vertices in one bucket and then run them in parallel. And then I can get some speed up. Okay, so that's all you need to know about this algorithm. Okay, so this is implementing this algorithm is a pretty interesting system work. Okay, so I didn't put this papers are, but some of them are in PLDI, some of them are in PACT or some other assistant conferences. It's very hard because if you think about it, at least some of the challenges are, how to maintain the dynamic set of the elements. So you look at all these sets, and then you drag these vertices into different buckets, and then you can drag the same vertices to different buckets concurrently. Okay, so that's very hard. If you think about how to implement such a data structure, that can be pretty challenging. All these concurrent updates, deletion, and insertions. So if you ask me how to do that, I don't know. I don't know a very good way to do that. That's why they propose all different ways to do so, but it's a very hard problem. Alternatively, I'll just let you know, so when you update a single bucket, you have to run it sometimes for over 100 rounds, okay? And then it takes forever, and then you have to run over hundreds of buckets. So some of these system works avoid to just synchronize because you have to do tens of thousands of synchronizations, which is slow. So they just don't really finish this round. They do some tricky things to keep moving on, but then you have to keep load balancing, and then there are a lot of tricks. It's like implementing a mini operating system. So you have a lot of tasks generating, and then you just want to run them. And another thing is the algorithm is very sensitive to the best value of delta. So if you just use another, if the best delta is, let's say 100, if you use 20, the performance can be 10 times worse. So it's very sensitive. So there are a lot of issues. People have been studying it for 20 years. I don't think we got very good outcome from that. So our question is, okay, why don't we just try something else? Okay, so if let's say we cannot solve this problem, then just try to solve it another way. So we can consider how do we do this? Okay,
Can
sure.
I ask a question?
Sure, sure.
So my question here is about when you say concurrent execution, is it within one bucket or across different buckets?
Across different buckets.
So it's like different buckets are simultaneously
So,
executed.
so you look at one bucket,
Uh-huh.
but then once you update your neighbor can go from one bucket to another.
another, yeah.
And then you can do for the same vertices simultaneous because this vertex may have multiple edges. So yeah, so maybe one of them is moving it from bucket 5 to 3, and then the other one is moving it from 5 to 2. So you want to make sure you don't have duplicates.
Mhm.
You do it correctly,
Mhm.
and you have quite a few things you
Got it.
have to
Got it.
guarantee. And while you don't know all these updates ahead of time.
Yeah.
They're generated on the fly.
Okay.
Yeah, so it's hard, okay, as you can imagine. So let's consider sequentially what can you do? Sequentially, you use Dijkstra's algorithm. That's very simple. Just this is pseudocode. If you implement it, just in C++, Java, pick your favorite, just use the standard library as a priority queue implementation. So you have a priority queue that maintains a set of vertices. Originally, you have S in it. And then you just every round you pop one element. Where's my mouse? Okay, you pop one element with the smallest distance, relax their neighbors, and update them in your priority queue. Okay, very simple. And the guarantee is that every vertices will be extracted only once. So you just run this algorithm super fast. But the thing is that it has no parallelism here. Okay, so there's a little bit parallelism. You can probably relax their neighbors together, but maybe usually on most graphs you have 100 to 1,000 vertices. This is very minimal parallelism you can use. And usually large scale graph have tens of millions of vertices to billions of vertices. You have to do all these vertices sequentially. So that is not ideal, but this very simple sequential solution. At the same time, I'm not sure how many of you have heard about it, but there's another algorithm called Bellman-Ford. It's a very simple algorithm. Again, well, it's even shorter, and you don't need any priority queue. You just maintain, again, this vertex set for all these vertices. And then instead of picking the one with the smallest distance, you just look at all of the vertices in this set F, and then try to relax their neighbors all at the same time. Okay, and then in this case, you have a lot of vertices, you're relaxing a lot of edges, you get a lot of parallelism. And then every round you do that, you have a very good parallelism. The downside is that it takes a lot more work because you have to look at every vertex in many rounds. And then, so it's hard to say which one is faster, the parallel Bellman-Ford or the sequential Dijkstra's algorithm. But yeah, so the short answer is we can simply combine them together. Okay, so in Dijkstra's algorithm, you pick one vertex from this set. And in Bellman-Ford, you just look at all vertices in this set. Okay, so in our case, we just say, okay, so if we want to get some parallelism, but without looking at all these vertices, because a lot of these work are wasted, what we're going to do is called a rho-stepping algorithm, which is very simple. So still look at this frontier, you pick row smallest vertices, because in that case, you can control, let's say 10,000 vertices, you relax their neighbors. Then in this case, you can get some parallelism, but you don't want to just update everyone's neighbor, because if a vertex is very, very far away from the source in the set, it's very likely that some other vertex will update it during this process. So if you use that to update their neighbors, you waste this work. In this rho-stepping algorithms, you look at the row smallest element from the set, so you get some controllable parallelism, but you don't look at the vertices that you don't have to look at. Okay, so that's all about this algorithm, pretty simple. And alternatively, if you still remember, we have this delta stepping algorithms. So you just look at, in the first round, you look at the vertices within distance delta, and then the next round, you look at 2 delta, 3 delta, So we just don't finish within a round. So we just here, we can do something similar. The first round, you look at all vertices with distance delta. In the next round, you have 2 delta, 3 delta, 4 delta. You just keep running that. Okay, so there's no rescheduling. There's no synchronizations between rounds. You can just simply do this. Okay, so if you think about this new algorithms, it's a relatively new algorithms, 3 years old. It's conceptually pretty simple. Okay, it's almost identical to Bellman-Ford or Dijkstra, the sequential algorithm you have learned. How can you implement this algorithm? The key thing here is to maintain this frontier set. And we realize that naively, you just use a bitmap. For every vertex, you just check if this vertex is in your frontier or not. Okay, so that is a easy way you can implement it. It's actually in our course project. Every student who take the course should implement it. Very simple. And then we realized that a better implementation, actually our best implementation among all the ways we tried, is just you use an array to maintain all these vertices. So every time you want to get the smallest 10,000 vertices or vertices within 3 delta, 4 delta, you just run a partition. Okay, it's a very simple parallel process. You can run it. So you get, and then you partition the groups into the ones you want to look at in this round, and all the other vertices you want to defer for the further rounds. Okay, so it's just very simple. If you take parallel algorithm course, the partition is something covered in the first week. And then it's just, if you know, this is called purely fork join. Everything we need is just a parallel for loop that is implemented in most of the parallel libraries. No complicated load balancing issue, no bucketing structure, no heuristic. Okay, that's all for this algorithm. And what makes it even more interesting is if you just compare between these two algorithms, the rho-stepping algorithm and the delta step algorithm, the only difference is just this line of code, how you grab the closest element. Okay, so you can actually abstract this, let's say as a function called extract. So I have a frontier. I just look at the first several vertices I'm going to process in this round. And actually, if you look at most of the existing parallel shortest path algorithms, they're all doing that, although no one has ever noticed the similarity between these algorithms. You just look at the closer ones. So at the very beginning, the delta stepping algorithm, you cut it into buckets, you update the closest one repeatedly. That's one of these examples. Okay, so all these algorithms are doing that. So we call the stepping algorithm framework. And then you can show, okay, well, it's not the focus of this talk, but if you want to get some fancy theoretical bound, you can design some data structures to do this extract efficiently. And then you can show some crazy bounds like this. I'm not going into the details, but you can consider all these algorithms together. And then if you can get some better parallel data structures, you can improve all these algorithms. I'm not going into the details. It's pretty boring, to be honest. The interesting part is we run this algorithm, compare with these highly widely used, widely cited graph libraries, and they all have the shortest path part. So if you take, so this is our first graph paper. So at that time, we only compared social networks and row graphs. In our later papers, if you go to, we test maybe 10 different types of graphs. But generally, you have these small diameter graph, social networks, and the large diameter graphs like row networks. So the graph algorithm can be drastically different, have different performance on different types of graphs. So we show that, on social networks, the diameter is usually between 10 to 100 and a lot of vertices. So in that case, the fastest algorithm is this rho-stepping algorithm. It's much faster than the existing ones. And on the road networks, because there's a road network, you have some geometric information. So for this delta star stepping algorithm, you look at delta 2, delta 3, delta, make sure that you search your proximity, and then you don't waste a lot of work going to a lot of vertices at the very beginning. And then the delta star stepping algorithm works the best for this type of algorithm. So here is a relative performance. Lower is better. And then this is the average of multiple graphs. And actually, we just test this algorithms on more graphs, and then it just follow, the small diameter and large diameter. So Although this is just for road networks and social networks, actually you can, depending on the graph, have small or large diameter, you will see similar result. And one more thing I want to mention is here we've just picked the best parameter, but for our own algorithms, you don't have to pick the parameters. Or if you look at 10,000 elements every round, that's your machine parameter. It's not related to your graphs. But if you want to run delta stepping, you have to find the best delta for every graph and every source node. But it's a chicken and egg problem, because if you know which parameter runs the fastest, you know the shortest path already, so you don't have to run it again. Okay, so yeah, so this is a very simple algorithm, and that's sensitive to the parameters. And if you want, you can see more result in our paper. So feel free to stop me at any time if you have any questions.
Yeah.
What changed exactly that you said that it has balanced workload among?
We just don't, every round we just, let's say in row stepping, we just look at the 10,000 smallest vertices with the smallest distance, and then in parallel update their neighbors. So you control the size so that you get sufficient parallelism, so you don't have this issue. Let's say in their work, if they just every round they look at the bucket, relax their neighbors, there's no load balance issue, because you have whatever number of vertices, you distribute them to the cores by some scheduler. You don't have to worry about it. OpenMP or whatever can do it for you. And you just run it, that's fine. The load balancing issue is in their algorithm, they just don't want to synchronize between the rounds, because in some rounds they can have 100 vertices, and then they just don't want to just stop and then run another, because there's some cost to just distribute this task to multiple processors. So they just try to say, okay, when I relax their neighbors, I just keep running without getting the next frontier. And then, but in that case, when I just keep updating some vertices, my own queue can get significantly larger. Maybe others have already finished. So yeah, I have to stop, redistribute the work, and do a lot of crazy things. I should have mentioned that more. So in our case, just look at these vertices, make sure it's a correct amount distributed to different processes, relax the neighbors, and come back. So there will be no such issues.
Yeah, so from the hardware perspective, that sounds like a synchronization cost is higher.
If you don't design the algorithm correctly, you
Yeah.
may end up with having too many little rounds. So you either need to synchronize, or you don't synchronize. You just let every processor do some crazy things on their own, but then you will have load balancing issue. So that's why, as I mentioned, those are mostly system works to deal with these things. But you can design a different algorithm that does not have these issues.
So I have a follow-up question. So you mentioned that you have to, your algorithm can automatically decide the parameters. So are those parameters, you have some heuristic algorithm to design them?
Good question. So for row stepping, just pick anything between 10,000 to 1,000,000 that give you almost identical performance. Because that's a machine parameter. You want to fill all the processes and relax their neighbors. It's not really related to the graphs. So you know what computer you're going to run it, but you don't know like the property of the graph. Once you run this algorithm, you know the property, you know the distance as well.
Okay.
That's the thing we say is less sensitive to the parameters. Yeah, thanks for the questions. Okay. Summary here, engineering the original delta stepping algorithm is very interesting system project. We show this new algorithms, very simple ideas, and it works pretty well. Okay, now let's move on. So this is the algorithm to compute single source shortest path. So let's recall the real world applications when we need shortest path. Okay, for example, if I want to use Uber, I want to check the cost to the airport, for example. In this case, I have a source, and also I have one single destination. Okay, that's usually the real world applications. So you don't compute the shortest path from UCF to Boston, every place in Boston. So now you have the additional information that you have a single destination. So how can that help? Okay, so there are some ideas, very old ideas, definitely older than any of us in this room, probably older than our parents. So you can do something better than running Dijkstra's. Okay, so the simplest thing is you have this graph, and then you start from the source node, you run Dijkstra. Once you touch and finalize the destination T, you can stop because every time Dijkstra pop the distance from your queue, then that is finalized. You don't have, it won't be changed in the future, so you can stop this algorithm. That's very simple, called early termination. There are some other ideas, also very old ideas, older than my parents at least, is that you can search from both the source and destinations. And then when these two searches, when it's two Dijkstra searches meet, and then I'm not going to the details, but the conclusion is that then you have the path computed. And then there's some simple way you can merge them. So you know the ST shortest path. And there are some other ways called A star, is that if you can estimate how far a vertex to the destination, then you can just guide the search to the correct direction. So something like that. So you're gonna look at fewer vertices with the prior knowledge, if you have the prior knowledge on how far you're to the destination. So this can be used in maps because you have some geometric information for these nodes. And of course, you can combine them together and get this so-called bidirectional A star. So I'm gonna look at smaller number of vertices. Okay, but if you think about all these algorithms, they are using Dijkstra's algorithm. Okay, so you have to visit all these vertices in their increasing final distances, which is not true in a parallel setting. Because in the parallel setting, you look at a subset of the vertices, relax their neighbors. You don't know which are siloed. Maybe you can check, but parallel algorithm doesn't check that because it doesn't give you any benefit. Because if for the vertices that have been finalized, they will not be updated in the future. So they will be not included in the future buckets. So yeah, so how can we do that? So it does not work directly in a parallel setting. So we show that how you can actually adjust this algorithm, make sure that you can run these like bidirectional searches, A star or bidirectional A star searches only with the tentative distance, not the final distances. Okay, so I'm not going to the details, but you just say it's doable. You have good performance compared to the sequential heuristics that can improve the search. We get almost the same speed up. So if the bidirectional search can make your algorithm 5 times faster, then our parallel solution can also be 5 times faster than parallel SSSP, something like that. Parallel rho-stepping. Okay, and another interesting point we show is that you can also extend to a batch of ST queries. So let's say you have 100 queries, then you can share some search space. Okay, so if you have more searches, you can have, it will be faster than running 100 searches on their own. Okay, and this is interesting work is under submission. So another thing is that is that all? So can we compute point-to-point queries even faster? Okay, so if you don't do anything, then these approaches, bidirectional search, A star is probably the best you can do. But if you allow some pre-processing, then humans are smart and not so smart. Smart is that people have been developed a lot of interesting ideas you can take use of. So I'm going to talk about how Google Map actually compute your shortest path. So let's say you have a graph, and then you run some pre-processing. And then once you pre-process the graph, it kind of build you a DAG. Not necessarily for this graph, it's just an illustration. A DAG, so all the points are having edges pointing down. Okay, so when you do a search, let's say for these two vertices, so this algorithm can guarantee that the path is always like you go down and reach a point and then go up. So like a V-type graph. So in that case, when you do the search, you just do the search downward. And then in most cases, they're not going to touch a lot of vertices, maybe tens or thousands of vertices, and then they will meet at some point and you can reconstruct the path. So this is called contraction hierarchy. So I'm not going to the details. It's very complicated. It's not this algorithm is younger than most of us, probably all of us, 2008, and the new algorithm, the finalized version. People have been spent maybe 10 years in developing the details of this algorithm. So in that case, the query can be super fast, like a millisecond level, even for, let's say, the entire map in the United States. Okay. But there's the issue. Okay, so once you have this graph, you can compute the shortest path pretty quickly. But constructing this graph takes forever. Okay, so I'm not sure. Hopefully, you guys do not have this experience. So when you drive in downtown LA, the traffic is very bad. So when you drive, Google Map will tell you, okay, there's a 25-minute slowdown on your highway. Try to exit in the next, use the next exit and use another highway, something like that. So you exit the highway, you drive to another highway, and then there's a 35-minute slowdown on this highway. Try to use the third highway. And when you go to the third highway, you're gonna have some issues like that because it's not really real time. So Google has a real-time traffic condition, but they cannot really compute the shortest path using this real-time result. I think it updates, like my own experience is maybe every 15 to 20 minutes, they're gonna readjust this graph and then give you the new distance. But then hopefully not the case here, but in LA, the traffic is so bad that 15 minutes can change a lot. So you cannot really rely on the live traffic. So, and then the main reason is to build this graph, it is again entirely sequential. They build one node at a time, like Dijkstra, they pop it, they do something, adjust the graph, and keep doing that.
Okay. Sure. So here, when you say building the graph, for example, it takes time to send an updated graph to the Google.
Yeah.
Is it down in the cloud or is it down in the client side?
I believe it's in the cloud. Yeah, because it's just too slow. Your phone will run out of power if you run this algorithm locally. Yeah. Yeah. So it just computes something in the backend and update it once in a while. This is my understanding based on my not so good user experience. So yeah, we need to make this better. So one thing we've shown that is you can make this sequential algorithm a little bit faster, maybe 4 or 5 times faster. But then we show how you can parallelize it, which will be another additional 40 to 50-fold speed up if you involve parallelism on a 100-core machine. I'm pretty sure Google has those machines if they want. So if you, for the same graph, the entire roadmap of the USA, our algorithm can rebuild this graph in like a minute. So in that case, I'm sure they have real-time traffic information. So if they can use our algorithm, we need to let them know you can just have much better real-time feedback if you're using Google Maps, especially in some cities with very bad traffic. And also this idea is actually general to other graphs. You have to change something, let's say for our social networks, because their graph topology is pretty different. But the idea is also usable just to build this DAG structure. Okay. And the last thing I want to mention just very, very briefly is how you can compute the shortest path from multiple sources. Okay. So theoretically, there are some algorithms 10 years ago, but it's too complicated, never used in practice. There's some practical implementations. If for some applications, you need to compute shortest path from multiple sources. There's some, they call it tricks. The difference is the tricks doesn't have any theoretical guarantee. They give you some performance gain. So we call it theory. If they can prove, it gives you performance gain. Okay, and then recently we realized that they're actually equivalent. So the tricks you actually use is the same as a super complicated algorithm that no one can implement. They have the same theoretical guarantee. So you can use this very simple trick. You can use to solve the shortest path from multiple sources. And then, shortest path is widely used. If you ask what are the applications with multiple sources, these are a lot of problems that rely on it. And then you can use the same tricks with some modifications and then to accelerate all these queries. The conclusion here is that's all I have for shortest path. Is for most of the algorithms and problems, how to design simple and efficient parallel solutions remains unknown. So if you're working on related areas, you should be able to find a lot of interesting topics to work on. Any questions to this part?
So
okay, sure.
One question, I'm not familiar with the bit parallelism. So you did trying to break down the computation at the bit level or?
So, okay, let me just explain a little bit. So this is another ongoing work. So my student didn't make the slides I can directly use. So here it means you have these different sources. So let's say in a priority queue, I want to know, so if vertex A is in my priority queue. So if you have multiple sources, what you can do is you can use every bit to indicate, okay, so this vertex visit me currently in the priority queue. So within the integer, I can actually store 32 or 64 bits to indicate if this vertex can visit me, the other vertex cannot. So if I'm in the priority queue, when I relax my neighbors, I can relax. I just look at all these edges once and then relax all the vertices that can touch me and relax my neighbors. So this kind of like a bit level trick. So we have integers in our computers, but we can use that to represent a lot of bits. And then that counts as one addition or a min operation, but it actually can do multiple updates simultaneously. Or you can compress. You don't need the number of sources multiplied by the number of vertices to show if you're in the priority queue or not. You just need n integers.
Right.
Okay, that's the bit level trick. Yeah.
So it's kind of transpose the operation from the original integer indexes into the bit level.
Kind of like that, yeah. So every time you relax, you're actually doing that for 64 sources,
Right,
not
right.
just one. So you can get some speed up, but the original theoretical algorithm was just too complicated. And then there's some tricks, just as I mentioned, you just maintain an integer, relax their neighbors simultaneously. We show that actually they have the same theoretical guarantee as the work done by the theory community.
I do hardware architecture, right? So I'm thinking, I also work a lot on the kind of bit level things.
Okay.
And I'm thinking, for example, is this kind of a support, architecture hardware support for this kind of bit level, the bit parallelism, how good it is? Or is there opportunity for potential hardware, let's say microarchitecture support to make it faster?
That's a really good question. Yes. So if you can, when we think about computer architecture, one extension we have the SIMD or vector unit. So in that case, you can actually pack more than 32 or 64. Our preliminary result tells that if you use that, that's even better because you're gathering more information. So unless you have very strange graphs, well, most of the graphs, the more you gather, the better you are. So having wider range could help. Although, this is mostly on the theory side. We show that, okay, you have the theoretical guarantee and it's applicable to other applications. But we do notice that the wider, the better. That's the short answer. Yeah, so I'm not sure for the other problems, but for shortest path, the wider, the better. So we
good fit if, for example, Google or Uber, such companies, and give them a choice, for example, special architecture support for such an algorithm is very valuable, probably.
That's a good point. Yeah, I didn't thought about it in that direction. That's why we have the talk.
Yeah, we
Think differently. That might
we can
be.
talk about it later.
Yeah, maybe that's something interesting. So we're mostly focused on this just shared memory setting and then how to do that.
Right.
But of course, yeah, as you mentioned, maybe some architecture improvement
could potentially
improve the performance. That's an interesting question. Yeah. So yeah, I'm going to be brief. Okay, so we also don't just show this path. We look at biconnectivity. It's just like you have a graph. Graph biconnectivity is you want to know if two vertices are connected and remain connected after you remove any single vertex. You can consider this a router network. Some router can die, but you want the system to be connected. For example, let's say U and R are not biconnected. If you remove S, they become disconnected, or R and X are biconnected because they have two paths. So a little bit delay in the animation. So no matter which vertex you removed, they remain biconnected. So this is pretty useful. One of the oldest algorithm people have been studied before we have computers. People would build telegrams back to 100 years ago. I've never seen any telegraph machine, but they need to consider this. So this is like a biconnected component, and you want to make sure you want to at least know what are the vulnerable point in a network. I'm not going to the details because it's a pretty complicated algorithm. You see, U and R are in different biconnect components. R and X are in the same biconnect component. So I'm going to be brief here. So we shown an algorithm. That was the best paper in PPoPP'23. So hopefully you believe in everything I've just said here, peer reviewed. So it's a very, it's a theoretically the best algorithm you can get in an n plus m optimal work. And its number of edges m is the number of vertices. You have to at least look at them all. And polylog span means it's highly parallel, the best parallelism you can assume, and then order of n extra space. Okay, so because of the simplicity and theoretical efficiency, this algorithm is very fast, scalable to different graphs, different number of processors on different machines. They significantly outperform all existing algorithm software. So we test almost 20 graphs in our original paper, and they got pretty good reviews. But one reviewer said, try these another 10 graphs to make sure that you didn't pick these 20 graphs. So we just add them. They're still much faster than the other. So they actually believe our experimental result. Of course, if your graph has 5 vertices, that has no difference. You have to, the graph has to be reasonably large. Let's say have 1 million vertices. Okay, and then this is very simple algorithm, although I just don't want to go into the details here. So that's one of the example. You can make significantly better algorithms, both theoretically simple and have good performance. Also, strong connectivity is you have a graph, in this case, a directed graph, and you want to compute the set of vertices. Don't read the text, it's long. You just want to find the vertices that A can reach B and B can reach A, so like this. So within one a strongly connected component, they can reach each other. And if they're in different connected components, either one can reach the other, but not vice versa, or neither of them can reach each other. The thing is that if you consider these as super vertices, and then you put all these edges between them, it becomes a DAG. So it will not have any cycles. So this is a graph is pretty good property. So you can do a lot of post-processing if your graph is a DAG, but you cannot do so if the graph is not a DAG. Okay. So again, how to do this algorithm in parallel remains unknown for forever. So Tarjan, if you know Tarjan, Bob Tarjan, he had the sequential algorithm back in the 70s, and then no parallel algorithm can beat his sequential algorithm, even though now we have over 100 processors. So we showed an algorithm back to 4 years ago, so you can do, well, I'm gonna skip the details, just let you see the animations. So you can start from one vertex, check all the vertices that this vertex can reach, like A can go to K, B, C, F, D, E, but not the other vertices. You can see which vertices can reach A, so you can get these 2 sets. And then you have 2 sets, you have 2 times 2 different cases. So if they can reach A and A can reach them, then they're in the biconnected components. That's the definition. And then what you can also do is you cut these edges, cut the edges between different components, because you can also show they will not be in the same biconnected component. So this is not done by us. Okay, people know that back to the last century, but they just don't know how to use this property. Okay, so and then in this case, the red one is in a biconnected component, and then you just recurse on the other 3 and keep running this algorithm. So the high level idea, okay, so I should run this. Okay, so based on the definition, the red one is a biconnected component. You can cut the edges if, let's say if they're not in the same group. We have 4 groups here, and then it just keep iterating. Okay, so the algorithm is randomly permute the vertices, run this 2 reachability search, get 1 SCC, and then cut the edges. Sorry about the delay. Okay, something like that. Okay, and then we show that this simple idea actually worked very well in parallel. You have to change something. One is you do multiple reachability search. So you can do 1 search and get these 4 sets. You can also do another search and get another 4 sets like that. And then you can do these 2 searches simultaneously and cut these edges at the same time. Okay, in that case, you just cut all the edges and then recurse. So you can do 2 vertices at the same time. And you can actually do more. In that case, you get more parallelism. Okay.
So I'm just starting for every parallel, like thread or every parallel process.
That's a very good question. Let me go to our final algorithm and you will see that. So again, we're gonna randomly permute the vertices, because otherwise you always have the worst case if you do these searches in a certain order. But you randomly permute that, and in our algorithm, we just pick one, do the search, and the next round I pick two, random one, do the search, up to two, because the one can be in the first SCC, you don't have to do that. And then you do 4 searches, and all the way to n over 2 searches in the last round. So in that case, I can only do these searches for log n rounds, which is a lot fewer, so you can get a lot of parallelism. How to distribute this? So you need a reachability search algorithm. So you can consider it similar to the breadth first search or depth of search or whatever search you want to you like. So that's a subroutine, so you can just directly use. So how to distribute the work? You need a multi-search algorithm from multiple sources. So that'll be, you can use some bit tricks. You can do whatever you like. So this is an application that can use the algorithm we mentioned previously. But here you don't need the distance. You only need to know if it is reachable or not. In that case, I make the problem even simpler, better for bit tricks. Okay.
So run twice, I would give like 2 different times for convergence because I'm randomly
Yes, because you're doing more, so you may need some additional effort to do that. So we control it carefully. We show that theoretically, this M log n work is the same as if you do it one at a time. But you have to do this in a 1, 2, 4, 8 way. You cannot just do n at the same time. That'll be too slow. So you have to do that in a certain way. It'll give you the optimal the work if you use this type of reachability algorithms, and you can get a lot of parallelism by running these reachability searches together. Okay, and then we implement this algorithm actually last year at Tsinghua, have a paper in Tsinghua, and show, because there are some details as you mentioned, we have to do this reachability carefully. In our theory paper, we just show you, if you have a reachability search, you can do that. You give you that theoretical guarantee, but how to implement this multi-reachability search, we show you can do this tricks. And then actually by adding all pieces together, we can get better performance. So this is a relative speed up of all graphs compared to the sequential Targent's algorithm. So 75 means 75 times faster than Targent's algorithm on this graph called Life Journal. Okay, and then there are a lot of graphs. And you can see the larger the better. So you can see our graph is consistently better than Targent's algorithm, except for one graph. We picked this deliberately because this is a very small graph. We want to test what is the boundary you want to use parallelism. This graph has about 1 million vertices. So if you have more than 1 million vertices, you should use our algorithm. But around 1 million vertices or smaller, maybe the sequential algorithm is still good. Okay, so the summary here. Okay, we talk about a lot of graph algorithms. So in the parallel setting, you probably all know it's a lot harder than the sequential setting. So if we want to design a good parallel algorithm or solution, what are the things we should consider? Or before that, let's think about what makes parallelism hard. So there are many reasons. I think one major reason is the sequential ideas are very simple. Okay, so if you take any undergraduate algorithm course, you talk about greedy, you talk about dynamic programming, all these ideas, you have for loops, you do something iteratively. They're so simple, just write a for loop and then do something. But they are sequential. Usually you cannot run the for loop just directly in parallel. So that's how we think algorithms, how we teach algorithms in undergraduate courses. And it's just so widely developed for 100 years, but they are not directly parallelizable. The other reason is sequentially, we have these priority queues. We have all these binary search trees, hash table, all these good data structures. We don't have them, or that we didn't have them in the parallel setting a while ago. Okay, so that might be some reasons. And there's some other reasons is parallelism come with a cost. That's probably even more, you probably know this even better than I do because you do architecture. So for example, some algorithms, more on the algorithmic point of view, is algorithms sacrifice space for better parallelism, but that may not be a good deal because if you cannot run it on a computer, you use more space than you have in a machine, then you cannot even run it. Another thing is that synchronization is expensive. So if you have frequent synchronization, it costs a lot. Okay, so if we make a summary here, these are the challenges we meet. Maybe you'll meet some more. So iterative instance of sequential algorithms. We need more data structures, space overhead, thread level synchronization overhead. So if we want to resolve them, they coexist for a lot of these problems together. So to overcome them, we need, consider if you have a sequential algorithm, how you can parallelize it, what if sequentially you have these data structures, what are they in parallel? And then if we want to design an algorithm, space efficiency, synchronization efficiency, how can we, understand them? Okay, so this is the other works I've done mostly in this framework. For example, I have a lot of papers in, how to modeling, let's say, synchronization, space usage, or some other newer models like the non-volatile memory and then the processing memory architecture we have recently. When you design algorithms on it, what are you actually optimizing? You can say, well, I can just take a monitor, look at the space, and then that would be my space usage. But actually, it's a little bit more complicated than that because I think you asked me quite a few questions like, how do I do this task distribution? I don't control it. Some software control it. So you need to understand how these software are doing to make sure that these hardware will not cost you a lot of additional space, which might be the case if you don't do it carefully. And it's not even in your code. The software will spend a lot of space if you don't use, you have to understand it. So also, let's say in some architectures, what are you actually optimizing? So you can do some analysis, prove that the algorithm works well for all inputs or certain inputs, but which, rather than just test some inputs. Okay, so that's the computational models that I've been working on recent. And the second thing is parallel data structure. As I mentioned, sequentially, they're so widely used. Sorry, I think I updated slides. Never mind. So sequentially, they're so widely used, but they don't exist in a parallel setting. In the parallel setting, I want to say, okay, I update a lot of vertices. Can I do that in parallel? So actually, this is my wife's PhD thesis. It talks about how you can build so-called collection data structure. Collection is list, queues, priority queue, set, map. They're all collection. It's the name for all of them. And then you can just use a binary search tree to support all these interface, and then you can do this batch updates very efficiently. Okay, and then batch insertion, batch deletion, you can union two trees, intersect two trees, difference, map reduce, single node operations, smaller than, larger than, range operations, everything you can do sequentially, you can do it in parallel. And that's a very interesting work. That's my wife's PhD thesis. That's why she got a lot more offers than I have when we are in the job market. And then we also, so the only part I was involved will make them purely functional. If you know programming language, there's some properties good to have, and we optimize the space. So we submit this paper to PLDI. And after that, we also look at the other data structures. So we have designed various priority queues. And then like Van der Boas trees, this is mostly of theoretical interest. And then some practical ones like KD trees, cover trees, if you know, they're more used in machine learning applications. And nowadays, the hottest topic is do this AN search in a deep neural network pipeline. So there's one party, you have to find these nearest neighbor search ones. Why are you doing this clustering? And then how you can maintain these data structures efficiently. And the last thing I want to mention, let me check that time. Okay, oh, it's 4 already. So let me finish quickly. So it's how to, if you have a sequential algorithm, how can you make it parallel? So at the very beginning, we look at some specific algorithms, and then you can make them parallel. And then later we just extend this idea. We solve some long lasting open problems and how to parallelize, like Denali triangulation, convex Hall. People don't know how to do that for a long time. And then our solution is take the sequential algorithm, make them parallel, something like that. And maximum independent set. And then more recently, we just keep extending, and we show that you can do edit distance. It's the best paper in ESA last year. And also this year, we showed that for general dynamic programming, you write these for loops, you run them step by step. For all of these algorithms, you can directly parallelize them. Okay, and it's some very interesting work. Finally, because you work on it as well, so a lot of machine learning algorithms, we will try to make them a lot faster as well. Okay, so the conclusion summary is that I plan to design these efficient algorithms with good theoretical guarantee, but more importantly, simple and practical in practice. The conclusion generally is that for most of the problems and the algorithms, how to design efficient parallel solutions remains unknown. I think a lot of you guys are doing, so just, you guys do not need to join. Yeah, you have already joined. So yeah, this is a very interesting area, and we have all done interesting works on that. So yeah, that's all for this talk. And yeah, this is for already, but if you have more questions or want to discuss more, I'm happy to stay here longer.
Sure.
Yeah.
Any more questions? Maybe I have one.
Sure.
So my question is, so all of the solutions are based on for CPUs, right?
Yeah.
Multi-core CPUs.
Yeah.
And is there any opportunities for the GPU side of it?
Yeah, that's a really great question. Programming on GPUs are harder than on CPUs. So you put just more restrictions, shrinks your toolbox. So that's how I understand it. So I work mostly on CPU so far because we don't even have the toolbox for CPUs. So let me first have this work done. I guess at some point, maybe I will take a look at the GPU solutions and see if these tools can be used on GPUs or people. I don't think so. I think you need to design different tools. So
Right.
that's my understanding. So we probably need to recreate the world for GPU computing as well, which may take a long time. I think my goal is I spent 10 years to create this world for CPU algorithms, and let's see, maybe I will move on something else, but maybe on GPUs. So yeah, that's my understanding. Definitely there are opportunities, but they're not simple. I think, and my conclusion is that you have so many problems you have to solve in one problem. So sometimes you just solve it for this own problems, but what we feel like is a lot of problems share the same challenge. So maybe you can just, for example, data structures. They all use the same data structure. You don't have to design a data structure for every application, although that has been what people have been doing for 50 years. So in the parallel world, they just design a data structure for this problem, but they don't have an abstraction and then discussion. So, and also you have some space concerns, synchronizations, things like that. So I think definitely there are opportunities, but they're also challenging. GPUs are more challenging than CPU. But maybe that's not a bad thing because that limit your toolbox. You can only pick from these tools and just build the algorithm in the best way. CPUs, you have more opportunities and then more directions you have to explore. So yeah, so definitely that's something interesting, although I just give a justification why I haven't done much on it yet. Yeah.
And maybe I have one more.
Sure.
So we're done. Another question is, what do you think? Do you have anything in mind? For example, computer architectures can do to make it better?
That's a really good question. I know that's what you think mostly in the architecture side. So let me just talk about what I've done. So we're doing the opposite thing actually. So I come to the computer architecture seminar because I've done quite a lot of things on architecture, but we're doing oppositely. So we're just look at what hardwares do we have at this point, talk to the hardware manufacturer, give us access, and we see, okay, if you want to design algorithm on top, what can we do? What can we do to adjust our algorithms and work well on these architectures? So yeah, I'm pretty sure that you guys work on architecture, think in the opposite direction. So what you can do to make certain algorithms faster. That's a very complicated question because once you change the hardware, you change the toolbox for the algorithm. side. So let's say, yeah, you can always say for the same algorithm, what architecture can you change to make it faster?
Yeah.
And our side, then once you change the architecture, we can redesign the algorithms. Maybe, and in many cases, the reason I believe we got these algorithms is people didn't think in this way because they didn't see the hardware we have 20 years ago. They didn't have it. They just imagined. So once you have some additional input, you may think differently. So yeah, so yeah, that's my answer is we think in the opposite direction. So
So maybe one idea in my mind is that every time, for example, when you say you want to improve your algorithm to fit the hardware, and then those parts you want to improve might be actually also the limitations of the existing hardware.
Yes. That's definitely true. My feeling is that improving the architecture is harder than improving the algorithm. So for algorithm, you write code. You can write the code whatever way you want, but for architecture, you have to probably if you want to, let's say, improve the bandwidth, you have to sacrifice something else. So so it's harder. So yeah, definitely. Generally, for parallel computing, the hardest part is the bandwidth. You probably know that. The better bandwidth, the better. But for specific algorithms, that's a good question because we don't think in this way. Is that we're thinking the opposite way? So we look at the newest hardware and see how to improve algorithms. So yeah, that's a good. Yeah, I can think about this question more because I never thought about it in this direction. Maybe I finished. Yeah.
Relocated.
Yeah. Okay.
Yeah, I think we can talk offline.
Yeah, sure. I don't have a good answer for that question.
Maybe we'll have it.
Yeah, I will think about it and see what. Okay. All right. Thanks everyone for coming. Yeah.
And I think that's it.
Okay, sure.
Yeah, thank you for joining us. And I'm sure